All right, after a lot of setup and kind of laying the groundwork and looking at a lot of things, we're going to actually start solving some kind of meaty, proper physics problems. So we're going to use everything we've learned as we jump into this. So our first example reads an Olympic class sprinter starts a race with an acceleration of 4.5 meters per second squared. What is her speed 2.4 seconds later? So working through our problem solving steps, we start by just summarizing what happens here. It's pretty easy because it's a single sentence. Someone's running and accelerating. Straightforward enough. Now we're going to sketch it. So we know that we've got two times involved. So we've got the initial time and 2.4 seconds later. So we're going to draw or sketch our setup. Now when you're sketching, physicists are lazy, physicists are not artists typically, so squares and circles are your friend. So this represents our sprinter, and we know that her acceleration is equal to 4.5 meters per second squared. So I'm going to label that on here. The acceleration is 4.5 meters per second squared. And an acceleration is a vector, so I do need to point it towards the right. That's the direction she's running. I've labeled the distance between her initial and final position so that I can put my time down here as 2 seconds. So I'm basically saying between this first and last thing is 2 seconds, sorry, 2.4 seconds. So we'll just kind of jam that in there, 2.4 seconds. And it seems like that's all we have, but implied here, when you start a race, what do you know about your speed? Well, your initial speed is 0 meters per second. And then what we're asking for is what's her speed later? So we're asking for what's the final speed? Well, I can't find final speed in any of my equations, but I can find the final velocity. So I'm going to label that on here as an unknown with this question mark. So this right here is a great example of a sketch for this problem. And you can see now that it has all the essential stuff and it tells what happens. Something started on the left here, it ended 2.4 seconds later to the right. It was accelerating the whole time, and eventually we want to figure out what the final speed is. That's the mark of a really good sketch on a problem that's very clear, is that you can just look at the sketch and you know what the problem is asking you to solve and everything that you know. So now we want to write down an equation that we think will be useful for this. So from my great experience with physics, I know that I want to use this right here. And I don't know, in my mind, kind of all the different algebraic manipulations of this equation kind of all live on the same synapse. So I'll probably, when I'm solving problems, write different equations at different times, but they're all just slight modifications, right? Because this is the same as v minus v naught equals a delta t. V equals v naught plus a delta t, and this is where we're isolating our final variable, which we've done. So now we've got v equals v naught plus a delta t. Notice I haven't plugged in anything yet. Now that it's isolated, I get to plug things in. So v equals 0 meters per second plus 4.5 meters per second squared times 2.4 seconds. Notice the units go in. The acceleration is not 4.5, it's 4.5 meters per second squared. And if we run this calculation, you'll notice the seconds will cancel with one of those seconds. And the final velocity is 4.5 meters per second times 2.4. I don't know what that is, I don't have the calculator, but you get the gist. It's going to be something over 9 times 9 plus 0.4 times 4.5, so it's going to be about 11. The final velocity is going to be about 11 meters per second. So let's check if that makes sense. 11, that seems reasonable. It's quick, but it seems fair. Like that is not something that's definitely a human can't run. It's got the right units of meters per second, because again, the meters per second squared times seconds gives us meters per second. And it's in the right direction. It's a positive number, and we had set positive to the right. You may not have realized that, but all of our vectors that were positive pointed to the right. So this looks great. Let's jump into our next problem. At the end of a race, a runner decelerates from a velocity of 9 meters per second at a set rate of 2 meters per second squared. How far does she travel in the next 5 seconds? What is her final velocity? So again, we're going to sketch our situation. Similarly, we have twice 2 positions in time that we're going to be talking about. So I'm going to label this like so. And she has some initial velocity that we don't know that we're wanting to find. So some initial meters per second velocity. Oh, we do know that. It's 9 meters per second. She has some final velocity that we want to find out. And you can see this is why you want to kind of constantly be referring back to your question while you're sketching. And I am making all sorts of mistakes here. This should be 5 seconds. And it's the acceleration is equal to, now here's the tricky bit. She's decelerating, so we want to write that as a negative 2 meters per second squared. I really don't like the word decelerate. We'll talk more about it in class, but the basic idea is it is perfectly fine to describe acceleration and deceleration with just the word accelerate. And sometimes you don't necessarily know whether something's accelerating or decelerating, so just saying accelerate is better. And when people say decelerate, they often think negative, but we'll see in class why deceleration is not necessarily negative. But for now, it is negative in this problem, but it may not be in all problems. So looking at this, we've got lots of V's, A's, and T's. So we're going to go again with V equals V naught plus A delta T. Oh, and we also want to find what's the delta X. How many meters? But first we'll start with this. So V is equal to 9 meters per second plus negative 2 meters per second squared times 5 seconds. V is equal to 9 meters per second times plus negative 10 meters per second. V is equal to negative 1 meter per second. So let's check that answer. Does that make sense? Meters per second does. That's good. Magnitude makes sense. 1, that seems reasonable. She was slowing down. It should be lower. But negative 1 seems weird because that would mean she's running backwards. So let's double check to make sure all our numbers are right. So we said the initial velocity was 9 meters per second. Yep. We said the acceleration was negative 2. Yep. And we said it was for 5 seconds. Yep. So running through. As far as me looking at it right now, I don't see a mistake. So I think this is just a weird question the way it was set up. But you'll notice that that negative was cluing us in to go back and double check because it looks like something was wrong. But it's just a weird thing where I guess she ran and then she turned around and started running or moving back. Let's go and figure out our position. So we want to find our change in position, and that can be found with V naught delta T plus 1/2 A times the quantity delta, or times the variable delta T squared. This is already isolated for delta X, so I can write that as 9 meters per second times 5 seconds plus 1/2 times negative 2 meters per second squared times 5 seconds squared. You'll notice the second squared will cancel with the second squared there. The seconds here will cancel with those seconds. And we get delta X equals 45 meters minus 25 meters, because then 1/2 times -2 is -1, and then 5 squared is 25, so 25 times -1 is -25. Delta x equals 20 meters. Does the units make sense? Yes, meters, great. Does the distance or the magnitude make sense? 20 meters? Yeah, like if they were running, it's totally reasonable to have run 20 meters in 5 seconds. And then, does the direction make sense? The positive, yes, because they were running to the right and just slowing down, so it does make sense that they should have a positive displacement. The next video will have 2 more examples, so you can check those out, or if you feel good, you can jump into doing some practice.